Hello, my name is Alex Wong, and I'll be presenting Learning Topology from Synthetic Data for Unsupervised Step Completion. This is a joint work with Safa Cicek and Stefano Soatto at the UCLA Vision Lab. In order to perform spatial tasks, such as manipulation or navigation, an agent is typically equipped with multiple sensors, such as a camera, range sensors, and inertial measurement units for perceiving the three-dimensional scene. However, the perceived scene may be sparse depending on the range sensor, for instance, a LiDAR, or if it is comprised of the set of points tracked by a visual inertial odometry system, or VIO. For example, on the left, we have a sparse point cloud captured by a LiDAR and projected onto the image plane as a range map or 2.5D representation from an egocentric point of view. And on the right, we have the sparse features tracked by a VIO system. To obtain dense geometry, one can train a network to fill in these holes or to complete the 3D scene by fusing together measurements from different sensors, namely camera and sparse range. To learn such a mapping, one can directly minimize the discrepancies between network predictions and ground truth. However, ground truth annotations are often unavailable, and when available, they are expensive to acquire. For instance, correspondences between the laser and camera images are manually selected for Velodyne to camera calibration. Also, after projecting the point clouds onto the image, ambiguous image regions such as windows and fences are manually removed. This is not scalable, so we forego these manual annotations as supervision and instead propose to learn cross-modal fusion by leveraging unannotated real data and the virtually infinite amount of synthetic data where ground truth comes for free. Unfortunately, there exists a covariance shift, mostly photometric, between synthetic and real domains, making it difficult to transfer models trained on synthetic source data to target real data. To generalize to the target real domain, we need to be invariant to domain-dependent variations or to adapt from one domain to another. This is a hard problem and also an open problem. Instead, one might observe that, unlike photometry, the geometry persists for a given scene across domains. So we can bypass the photometric domain gap altogether by learning the association not from photometry to geometry, or from images to shapes, which require a high-level understanding of the semantics of objects, but from sparse geometry, such as point clouds, to topology by using the abundance of synthetic data. And in doing so, we can bypass the synthetic to real domain gap without having to face concerns about covariance shift and domain adaptation. But can we learn to infer the dense topology of the scene given only a sparse point cloud? For example, on the left, we have an RGB image, the middle, the full set of sparse points detected by a VIO system, and on the right, the target dense topology of the scene that we want to recover. Now, this is an ill-posed problem, as there exists infinitely many possible scenes compatible with the missing depth measurements or the holes in the sparse depth map. To do this, we need to learn a representation of the sparse points that can capture the complex geometry of objects populating the scene. However, this is a challenging problem precisely because the input is sparse. For example, the point cloud produced by a LiDAR covers approximately 5% of the image plane and only 0.5% for points tracked by a VIO system. And that is if we're being very generous. This renders the conventional convolutions ineffective because convolving a kernel over the sparse inputs will yield mostly zero activations. In order to process the sparse inputs, the kernels in the earlier layers are wasted on densifying the features to propagate the signal. For example, in the top row, we have the sparse point clouds from a LiDAR projected onto the image plane. And on the bottom row, they're activations after the first convolutional block of a deep neural network. The resulting feature maps are a little denser, but still sparse. So, to process sparse inputs, one would either need a very deep neural network with many layers or some complex sparsity invariant operations. To tackle the sparsity problem, we propose our version of the spatial pyramid pooling, or SPP for short, designed for sparse to dense step completion. Our SPP module performs max pooling with various kernel sizes to densify the inputs and to capture different receptive fields as shown in the middle block. But of course, when pooled with small kernels, the details of the sparse inputs are preserved, but the subsequent layers will produce very few non-zero activations. And when pooled with large kernels, the inputs are densified, but the details are lost. To balance details versus density, we weight the output of the pooling with several stacked one-by-one convolutions so that the network learns to optimize for this trade-off. To learn a representation of the sparse point cloud that can capture the complex geometry of objects, we introduce ScaffNet, an encoder-decoder network augmented with an SPP module. To train ScaffNet, we leverage synthetic data where ground truth dense step comes for free and minimize a normalized L1 loss between the prediction and ground truth. On the right, highlighted in yellow, we show the effects of our SPP module. And as we can see, a ScaffNet augmented with SPP recovers more of the biker than ScaffNet without SPP. Moreover, in the bottom panel, we demonstrate the effects of SPP on densifying sparse inputs while retaining the fine-grained details of the scene. In the middle, we have again the features outputted by the first convolutional block. And on the right, we have the features outputted by SPP to be fed into the rest of the encoder-decoder structure. And as we can see, the feature maps produced by SPP are much denser even before reaching the rest of the network. But because the estimated topology is only informed by a sparse point cloud, if there are very few points or no points at all, then we can expect the performance of ScaffNet to degrade. This is where the image comes back into the picture. We propose a second network that refines the initial estimate by incorporating the information from the image to amend any mistakes. Here, we show our full inference pipeline. First, ScaffNet estimates an initial scene topology from the sparse point cloud. Then, FusionNet performs cross-modal fusion and learns an element-wise multiplicative factor alpha and an additive residual beta from the image to refine the coarse topology estimate. Unlike previous works that learn a direct mapping from the image in sparse depth to dense depth, by learning alpha and beta around the initial estimate, we alleviate FusionNet from the need to learn depth from scratch, and this allows us to achieve better results with fewer parameters. The effects of the refinements are highlighted in red. While ScaffNet can capture the geometry of the printer, it incorrectly estimates the cabinet and the wall due to the lack of points in those regions. Hence, FusionNet amends them using image information and corrects the shape of the cabinet and wall. We note that FusionNet is positive congruent and only modifies the initial estimate in regions incompatible with the image while preserving the rest of the scene. Unlike ScaffNet, FusionNet is trained on real data using unannotated images and sparse point clouds. During training, we assume that we have access to a dataset of image sequence I and the associated sparse depth Z0, which allows us to leverage image reconstruction as a loss for supervisory signal. To construct this loss, we will need to compute the relative post G between the image at the current time frame I sub t and a temporally adjacent frame I sub tau. The relative pose can be obtained directly from a VIO system, and in the case where VIO is not available, we can incorporate a pose network to jointly learn depth and pose as shown in the diagram. Using the estimated depth and relative pose, we can reconstruct I sub t from I sub tau by reprojection, which will let us construct a photometric reprojection consistency loss as our main training signal. To learn alpha and beta, we minimize a linear combination of photometric consistency, sparse depth consistency, local smoothness, and a topology prior consistency term that constrains alpha and beta to be small. We note that the topology prior is conditioned on the local photometric residual by a weight matrix W, so that it selectively regularizes the output depth based on the compatibility between the initial estimate and the image. In other words, we only regularize if the reprojection error of the initial estimate is low. Otherwise, FusionNet has the freedom to modify the output of ScaffNet. And by minimizing this term, FusionNet learns to amend regions that are not compatible with the image while preserving the rest of the scene. Here, we show qualitative results on Kitty, an outdoor driving dataset. Our method can capture the shape of complex objects populating the scene. On the left, we see that we're able to recover the shape of pedestrians in dynamic scenes. And on the right, we show an example of the predicted depth back projected to 3D as a point cloud and colored. As we can see from the motion, our method also successfully recovers the shapes of cars, buildings, and trees in the outdoor driving scenario. Here, we show quantitative results on the Kitty dataset. In the top table, we compare our method against the state-of-the-art on the Kitty validation set. We note that ScaffNet only uses sparse depth as input and is trained on synthetic data. It is also lightweight and only contains 1.4 million parameters. Despite this, ScaffNet still beats some of the existing method with much larger model sizes that uses both image and sparse depth as inputs and are trained on real data. This is made possible by learning the association of sparse geometry to dense topology. And in doing so, ScaffNet can be trained on high-quality ground truth synthetic data and bypass the photometric domain gap, allowing it to generalize to real data sets. This demonstrates just how promising it is to leverage synthetic data to learn prior on shapes. And if we take a look at FusionNet, it is the fastest method using the fewest number of parameters, yet achieves the state-of-the-art on the Kitty benchmark. And on the bottom table, we also see consistent results on the official Kitty online test sets. Now we demonstrate our method on the void dataset. Having a learned prior on the shape of objects populating a scene is even more important for the indoor scenario. Indoor objects tend to have more complex shapes with many textureless surfaces, which locally don't give any information about the scene structure. On the left, we show that our method can capture the shape of benches, flower beds, cabinets, and printers. And on the right, we show that we can also recover textureless walls, tables, and challenging objects like thin chairs. Quantitatively, ScaffNet on its own already outperforms all competing methods that uses both image and sparse depth as input. And unlike the outdoor driving scenario, where ScaffNet is trained on virtual Kitty, a synthetic dataset with similar scenes as the target real dataset, Kitty, here it is trained on SceneNet, a dataset comprised of randomly generated household rooms where the scene distribution is very different from that of Void, which is comprised of classrooms, gardens, and laboratories. Despite the mismatch in scene distributions, ScaffNet still generalizes very well to Void, and this shows that ScaffNet learns shapes and not scenes. Furthermore, FusionNet improves the results of ScaffNet to achieve the state-of-the-art. On the bottom figure, we show a sensitivity study for various density levels of input sparse point clouds. As expected, the performance of ScaffNet degrades when we reduce density by about 10 times. This is precisely why we have FusionNet, so that we can learn the residual over the initial estimate by incorporating information from the image. But of course, as the quality of the initial estimate degrades from the decrease in density, FusionNet degrades as well, but it does so gracefully. With a 10 times decrease in point cloud density, FusionNet only drops by about half in terms of MAE. Because ScaffNet is only informed by the sparse point cloud, one may also wonder how sensitive it is to the mismatches in distribution of sparse points observed between a synthetic domain and the target real domain. In the top table, we compare ScaffNet and a subsequent FusionNet trained on SceneNets using random uniform sampling and corner-based sampling. All of the models were tested on the void dataset where the points are tracked by a corner detector. As we can see, ScaffNet exhibits some sensitivity to the mismatch in distribution of sparse point cloud. This is expected because the point clouds are so sparse, occupying less than 0.5% of the image space, such that the different sampling strategies would yield very different sparse 3D structures. However, once we obtain a dense representation from ScaffNet, we can see that FusionNet is not sensitive to the change in sparse points distribution. This demonstrates the benefits of learning a dense topology from sparse geometry first, which can help reduce the sensitivity of the downstream model to different point cloud distributions. However, we must note that if we were to use the same sampling strategy in both synthetic and real domains, then we can get slightly better results. Here, we consider transferring our model from Void, a dataset of classrooms, gardens, and laboratories, captured with an Intel RealSense, to NYU V2, which contains household rooms, commercial offices, and shops that were captured with a Microsoft Connect. On the bottom table, we show how well our method can generalize to a new dataset and how quickly it can adapt to different scenes captured by different cameras and range sensor setups. First, we compare our method, marked in green, that have not been trained on NYU V2 against the Paragon performance, or one that has been trained on NYU that's marked in red. Even though our method has not been trained on NYU, it still performs reasonably. One thing to note is that ScaffNet trained on CNET actually performs better than FusionNet trained on Void, and this is because of the photometric domain gap between Void and NYU V2. But it also goes to show, again, that ScaffNet can bypass the photometric domain gap. Now let's consider the rows marked in blue. After fine-tuning on NYU for one epoch, FusionNet quickly recovers performance, and if we were to train for longer, there is little difference between the fine-tuned model and the Paragon performance. This demonstrates the potential of unsupervised learning that enables our model to be deployed on different camera and range sensor setups and adapt to novel data sets with different scenes. So, we have proposed a method for learning a representation of sparse point clouds from synthetic data. We show that geometry, unlike photometry, persists across domains for a given scene. And by learning a map from sparse geometry to dense topology, we can bypass the photometric domain gap, which allows us to leverage the abundance of synthetic data to learn powerful representations without needing to worry about the covariance shift. But it is not perfect. ScaffNet exhibits some sensitivity to different density levels of the input, so we have to reconcile it with the image by using FusionNet to learn the residual over the initial estimate. We also didn't consider a case where the shapes in the synthetic data are not representative of those in the real data. So this is a first step, but overall, our results have demonstrated that this is a promising direction, and we hope that our findings can motivate more exploration into incorporating synthetic data into multi-sensor fusion pipelines for 3D reconstruction. For those interested, we have open sourced our code on GitHub and can be accessed via the QR code or the link above.
Hey everyone, thanks for watching. If you're interested in learning more, you can find the links to the paper and code in the description. And if you enjoyed this video, make sure to click the like button and subscribe for more content like this.